Hello everyone, good to see you again. I hope all you are doing very well. In this video, I'm going to introduce a basic model of aggregate demand, the level demand model. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I'm going to first introduce the concept of elasticity and level of demand models. Then, I'm going to present how demand, revenue, and profit curves look like under a level of demand model. Once we successfully estimate the demand curve, we can find the optimal price point where the profit is expected to be maximized. And I'm going to show how to find the optimal price under a level of demand specification. Last, I'm going to briefly talk about what there are competitors. Okay, are you ready? Then let's get started. Demand is a function of firms' actions and environment. Actions in marketing problems are associated with these 4 P's. First, product. Product features, design, brand values, and the others affect the demand. Simply, the better product, the more demand. Second, price. This doesn't include any additional price for transaction. It indicates only the unit price of the product. In general, the lower price, the more demand. Third, place. It is about where the transaction happens. Even though the product quality and price are really good, demand could be low if it is difficult to buy. Fourth, promotion. This includes all of campaigns and activities to promote sales, like price discounts, coupons, advertising, and so on. Decisions about these 4 P's determine the demand of a product, given environment. A typical example is seasonality. Beer demand in summer is greater than winter, but soup demand in winter is higher than summer. The demand change due to seasonality leads to firms' strategic decision making. An example is airfares in the peak season. In the peak season, demand rapidly goes up, thus airlines increase airfares to have more profits. Also, seasonality affects consumer response to the firm's decisions. In the tax return season, people tend to spend more money for non-essential products. And seasonality sometimes changes consumer behaviors. For example, during a sports event, people are going crazy and tend to make more impulsive purchases. There are also supply-side environmental effects. An example is price shock. An important component that determines airfares is oil price, finally affecting flight demand. Another example is technology shock. A technology shock usually becomes a game changer. For example, development of flash memory removed CD drives and DVD drives from computers. In sum, demand is a function of actions given environment. That is, to make accurate predictions, we have to know how demand fluctuates according to environmental changes and how demand responds to the marketing actions. Here is an example. Beer. For simplicity, suppose that we are focusing only on price effect. Just ignore all the other actions. Then, this would be the simplest form of beer demand. Demand is given by baseline plus beta times price plus extra demand in sum. Here, baseline and extra demand in summer reflects the seasonal difference, and beta times price captures how demand responds or price change. Without knowing those components, our prediction would be inaccurate. In this lecture, we focus only on the first component, the demand response to the action. The second component, environment, will be discussed later. Then, how to measure the response to price component? One method is to think of an absolute measure. How many units would be purchased more if we dropped the price by $1? Another method is using a relative measure. What would be the percent change in demand if we drop the price by 1%? The latter, relative measure, is called elasticity. In economics, the relative measure is more widely and more frequently used than the absolute measure because the baseline demand dramatically varies across products, and thus, using the absolute measure often leads to a comparison of apples to oranges. The concept of elasticity is not limited to price. For price, it is called price elasticity of demand. It is generally negative and usually measured by the percent increase in units sold where price decreases by 1%. For ad spending, it is called advertising elasticity of demand. It is generally expected to be positive and usually measured by the percent increase in units sold when ad spending increases by 1%. Elasticity has a mathematical property. The percent change in demand over the percent change in action variable is mathematically identical to the absolute change in log of demand over the absolute change in log of action variable. This leads to the following model, which is called a log demand model. Suppose that we focus only on the price effect, then a log demand model is log of demand is baseline plus beta times log of price plus extra effect of control variable. Here, the value of this beta is the price elasticity of demand. The size of beta indicates how people are sensitive to a price change. In general, the price elasticity is negative, and if it is exactly equal to -1, then we say the demand is unit elastic. This means the demand would drop by as much as the price increases by. But if it is greater than -1, then we say the demand is inelastic. This means changes in price cause a disproportionately small change in demand quantity. Goods with such demand pattern are labeled as price insensitive, and they are typically essential goods that consumers have no substitute for, such as water, gas, medication, and etc. But if the price elasticity is less than -1, then we say the demand is elastic. This means changes in price cause a disproportionately large change in quantity demanded. Goods with such demand pattern are labeled as price sensitive, and typical products and services with various substitutes are these type of goods, such as restaurant meals, fashion items, and etc. Here is an example of inelastic demand. This table shows the estimate of price elasticity of crude oil demand across 23 countries. The model used for estimation is a log demand model. The dependent variable is dt, which is the log of per capita demand of crude oil. And it is regressed on the log of crude oil price, log pt, the log of real GDP per capita, log yt, and the log of the lagged demand, which is a contract for the long-run equilibrium. Then the coefficient beta is the price elasticity of demand. The shaded column presents the estimate of the coefficient beta across the countries. As you can see, all values are greater than -1 and very close to 0, implying that demand for crude oil is extremely price inelastic. Now, I'm going to show a demand curve of an elastic product to illustrate the model's properties. For gravity, D stands for demand and P stands for price. Then, a simplest log-log demand model looks like this. Log D is alpha plus beta times log P. Taking exp, which is the inverse of log, this equation is equivalent to D is exp of alpha plus beta times log P. By definition, this equation is equivalent to D is e to the alpha times p to the beta. Here, this e is a constant which is called Euler's number. This constant is an infinite decimal close to 2.718. This graph shows the demand curve with alpha is equal to 8 and beta is equal to -1.5. Beta indicates price elasticity of demand, that is, percent change in demand over percent change in action, as in this example. Let's compute the elasticity on the graph. At $2, demand is about $10.54, and at $1.98, which is the 1% discounted price, demand is about $10.70. Percent change of price is just 1%, and percent change of demand is now 1.52%. At $4, demand is about $3.73, and at $3.96, which is the 1% discounted price, demand is about $3.78. Percent change of demand in response to the 1% price discount is 1.52 here. This is a little bit larger than 1.5 because the exact elasticity must be computed through continuous compounding. Then, what if price is equal to 1? When price is $1, demand becomes e to the alpha. In this graph, demand is about $29.81, which is e to the 8 when price is equal to $1. Then, what about the revenue? Revenue is, by definition, given by demand times price. Then, let's compute what would happen to revenue with the 1% price change. With the 1% price change, demand changes by beta percent. With a simple algebra, we have revenue that changes by 1 plus beta percent. Keeping this in mind, and let's look at what would happen. Here are two graphs. The left graph shows demand curves with various elasticity values. Blue curve is an elastic demand curve where beta is -1.5, and red curve is an inelastic curve where beta is -0.7. Black one is a unit elastic curve where beta is exactly equal to -1. You can see the elastic curve shows much larger demand drops in response to price increases than others. And how about the revenue? From the equation, beta of the elastic demand is less than -1. Thus, 1 plus beta is negative. This means increasing price always leads to decreasing revenue. Intuitively speaking, if demand is elastic, people are sensitive to price. So the loss in demand is larger than the gain from the price increase, leading to the decreasing revenue curves. For inelastic demand, beta is greater than -1, thus 1 plus beta is positive, and increasing price always leads to increasing revenue. Intuitively, if demand is inelastic, people are not sensitive to price. So the loss in demand is smaller than the gain from the price increase, leading to the increasing revenue curve. For unit elastic demand, beta is the same as -1, thus 1 plus beta is 0. This means the revenue is constant over the prices like this flat revenue curve. In this case, the loss in demand is the same as the gain from the price increase, so the revenue curve becomes flat. Then, what about the profit? Profit is, by definition, given by demand times margin per unit. Denoting C, the unit cost, the margin becomes P minus C. Then profit is given by D times P minus C. Here, the change in margin is always larger than the change in price. If price changes by 1%, the margin changes by more than 1%. This graph shows profit curves derived from the demand curve in the previous slide. Here, the unit cost is assumed to be 70 cents. As you can see, both inelastic and unit elastic profit curves show an increasing patterns of profit as price increases. This makes sense for the inelastic case because the revenue is increasing as price increases. And it also makes sense for the unit elastic case because the gain from the price increase becomes larger with the consideration of cost. However, if demand is elastic, the profit curve shows a different trend. When price is low, the gain from the price increase is larger than the loss in demand, and therefore the profit increases. But as price is getting higher, the loss in demand becomes larger and exceeds the gain at a certain point. Then, after the point, the profit becomes decreasing as price increases. For the elastic demand case, an interesting question is find the price where the profit is expected to be maximized. As shown before, the log demand model can be written as D is equal to E to the alpha times P to the beta. We call this a demand function with price as the function argument. That is, the demand is given by a mathematical formula with respect to price. For simplicity, let f of p denote this demand function. Here, the symbol with 3 lines is the definition symbol, meaning that f of p is defined as the formula. Because we are investigating the demand and profit for the elastic demand case, beta is presumed to be less than -1. Then we can do counterfactual for profit conditional on price. If the price is P and the marginal cost is C, profit is given by demand times the price minus the marginal cost. Because Demand is defined as function f of p. Profit becomes f of p times p minus c. This is the profit function with price as the function argument. For simplicity, let g of p denote this profit function. With the profit function, we can generate the expected profit value given a price value. Counterfactual with the profit function enables us to find the price point where the profit is expected to be maximized. We can compute the expected profit values with all possible price values and find the maximum, though. There is an analytic solution to get the exact maximum using the first order condition. Mathematically, this maximization problem is written as follows. We want to maximize the profit with respect to price. So, max indicates this problem is a maximization problem. And each subscript p implies p is our focal variable in this maximization problem. That is, the maximization problem is with respect to p. After the max symbol, we specify the objective function to be maximized. The maximization problem is with respect to p, so the objective function must be a function of p. We are going to maximize profit, so g of p is the objective function. Now, we know that g of p is given by f of p times p minus c. With some regularity conditions, the maximization problem can be analytically solved by the first order condition. The profit curve for the elastic demand shows an inverted U shape. That is, the curve is concave down. In general, a concave down function satisfies the regularity conditions for the analytic solution. The first order condition is that at the maximum, the first order derivative of the objective function with respect to the focal variable becomes 0. The objective function is the profit function, and our focal variable is the price. So, the first derivative of the profit function with respect to price becomes 0 at the point where the profit function is maximized. That is, dg over dp, which is the mathematical expression of the first derivative, equals 0. Solving the first derivative with the profit function formula, we have an equation. The first derivative of the demand function times p minus c plus the demand function equals 0. Solution of the equation is straightforward. We know the demand function f of p is e to the alpha times p to the beta. Its first order derivative is given by e to the alpha times beta times p to the beta minus 1. Then, plugging the function and its derivative into the first order condition, we have an equation of p e to the alpha times beta times p to the beta minus 1 times p minus c plus e to the alpha times p to the beta is equal to 0. Solving the equation with respect to p by rearranging the terms, we have the price point where the profit is expected to be maximized. That is, when price is beta over 1 plus beta times c, the profit is expected to be maximized. Now, let's graphically investigate the analytic solution of the profit maximization. This is the same profit curve graph as before. And let me enlarge this part for the profit for the elastic demand case with prices in between 1 and 3. Then we can find the maximum value of the profit. The maximum value is about $13.71 when the price is equal to $2.1. I have manually found this point, and the analytic solution from the first of the condition is exactly same as it. From the first of the condition, the maximum of profit is given when price is equal to beta over 1 plus beta times C. Because beta is minus 1.5 and C is assumed to be 0.7, the profit is maximized when price is equal to $2.1 as the same as in the graph. In most cases, we have competitors in the market, and the competitors' actions also affect our product's demand. For example, let's think about Tropicana and Simply Orange No Pulp Juice. These two brands are major players of the classic orange juice market. Suppose that we are Tropicana marketing team. When we drop Tropicana price by $1, its demand definitely increases. But what if Simply Orange also drops its price by $1 when we drops? Still, we expect some increase in demand, but definitely less than our expectation with Tropicana discount only. Mathematically, a competition effect is described as another term in the model. Now, we have two different brands, Tropicana and Simply Orange. So I'm using two subscripts, TR and SO, which stand for Tropicana and Simply Orange respectively. Then, those betas indicate the overprice elasticity of demand for the brand. That is, percent demand response to percent change of our product price as discussed. And those gammas indicate the cross price elasticity of demand for the brand. That is, percent demand response to percent change of the competitor's product price. We can do counterfactual even with the competition. From the estimated demand curves with cross-price elasticity terms, for example, we can draw a table of multiple price discount scenarios. Here, the two rows respectively stand for no price discount case and 10% price discount case for Tropicana. And the two columns stand for the same cases for Simply Orange. Then, the cell of the first column and the first row indicates the scenario where both brands do not have price discounts. In this case, the demand for the brand is given by 1597 units and 1537 units. In the cell of the second column and the second row, the demand for the brand are calculated when both brands cut the price by 10%. Due to the price cut, demand for both brands increases. In the cell of the second column and the first row, we have demand quantities when only Simply Orange cut the price by 10%. Due to the price cut, demand for Simply Orange increases, and the demand for Tropicana decreases compared to the no discount scenario because of brand switching from Tropicana to Simply Orange. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.